our next one. John Collins from AquaBlok is going to be presenting some case studies on remediation of shoreline and sediment sheens. So John, you ready to go? All right.
All right, thanks much. I guess to start off, I have an important observation here that maybe escaped the group, is that if you're talking about ASTM standards, you have to wear a tie and a suit coat. And if you're talking about remediation, it's okay to come up in just a shirt. So I think that's a good distinction here that I'm drawing. I'm going to switch gears. As Tripp mentioned, I'm going to talk about not only materials to help implement remediation, but also going to talk a little bit about specific case studies. As Tripp mentioned, I'm going to show some actual case studies. So the good news is that you get pictures. You get pictures of mud and other good stuff here going on. So the topics for discussion here. The problem I'm talking about, similar to what Joe just talked about, residuals. Residuals in a different way, a little bit different way, but still the same concept. And as I mentioned, I'm talking about materials here. So I'm going to go through a little description of what those materials are and what they do and how they work, and how they might be integrated into different types of remedial solutions. And then I'll go through some of the examples as well. So the problem here that I'm discussing specifically, but relates directly to what Joe just talked about, is this concept that you're going to have residuals. Obviously the goal of any remediation is to eliminate the sources of contamination first. And in the case of MGP, most of the time, the upland work is done, prior to getting into the water, just to make sure that you're limiting, ongoing, sources of contamination. But there's also, residuals in the sediment, post dredge, as we just talked about. Overall here, we're trying to reduce the risk of remedy. We're trying to implement materials that maybe help you reduce the risk of remedy. These tend to be fairly significant remediation efforts that are pretty expensive. So I'm just going to talk about a range of different approaches that may help us accomplish that. So first, as it relates to materials specifically, there's two types of materials, and I'm not just going to talk about our materials. I'm going to, mention some other approaches as well. But as it relates to the materials that we provide, we have two different groups of materials. We usually separate them into AquaBlok, which is our namesake product, but that's a low permeability. It's a chemical isolation barrier type of material. The idea is it's going to stop migration of contaminants without also allowing water to flow or whatever else happens to be there. But then we have another group of materials which we refer to as AquaGate, which are sorptive treatment materials, and those materials remain permeable, so they will allow water to flow through. And you'll see that we use these materials both in combination or one or the other, depending on what it is that we're trying to accomplish. So this is just a quick overview of the low permeability material. This is, again, the AquaBlok material. It's been applied at a wide range of different MGP and petroleum related sites, as well as for metals and PAHs. This is a product that's been around now for 25 years and has been applied very widely. The AquaGate materials, on the other hand, are newer, relatively speaking. They consist of a range of different types of usually sorptive materials that are intended to remove contaminants as they flow through the water. And we have, different types of materials. It's always AquaGate plus whatever that particular sorptive material is that you're trying to implement. Could be activated carbon, could be organoclay, could be a range of other types of materials. But I'm going to focus for purposes of this morning on organoclay, because that's one of the primary materials that's used for NAPL and for Sheen producing sediments. There is a little data in here about AquaGate plus PAC as well, but typically we use activated carbon for dissolved phase PAHs as opposed to pure phase or NAPL. So this slide gives you a little bit of, I think, really comparative data. If we look at organoclay versus activated carbon versus just native sediment or sand, in the case of the example that Joe just provided, when he talks about cover materials, generally speaking, we assume you're talking about sand materials. They have very little in terms of absorptive properties when you use those as cover materials. And again, the reason that you would use these types of absorptive materials is to reduce that risk, right? Reduce the risk that you would get any movement of the contaminants through those cover layers. So again, it's a risk of remedy concept. So we did some testing to take a look at organoclay in particular, and this was pretty interesting. We did a large project on the East Branch of the Grand Calumet River, and the idea here was to take a look at not only just the raw organoclay and how the material would perform, you know, for a number of different contaminants of concern, but also to look at, okay, so we're taking that organoclay product and we're making it into something called AquaGate plus organoclay. And so how does the organoclay perform once we convert the raw material into a product? And then probably more importantly than that, so then we're going to take that material, we're going to drop it in the water, we're going to create, you know, a layer that is intended to limit the migration of those contaminants up through the sediments and into the water column. So then the question becomes, once that material is placed, what are its characteristics? So in cooperation with Setco and Danny Rybel and others, we went through a whole series of tests, and this data was collected blind. So everybody that tested the material didn't know which was which. Okay, they didn't know whether they were looking at the raw as manufactured product or if they were looking at a product that actually came out of the river after it was placed. So the data that you see here is interesting data. It basically says that once you place these materials, it gives you a high level of confidence that they're going to perform the way you expect them to perform. And we thought that was a really good data set and very useful for everybody. And there's also, you know, KD values here, which are good for modeling if and when you get to that point. Okay, so enough about the materials. On to, you know, some examples. And what I did here with this approach is I wanted to talk about basically different configurations, different ways that the materials could be used and implemented into remedies as a way to illustrate what you could possibly do. So I broke this down into basically different approaches, what I'm calling approaches or methods where the materials may be applied. And the first one is something, oops, wrong button. The first one is something that everybody, I think, knows and understands relatively well, this concept of a permeable reactive barrier. And the idea is that, you know, you've got some amount of contamination that's, you know, flowing through subsurface. You don't want it to get to the surface water. And so you can put some absorptive material within a barrier wall that will intercept that contamination. So a couple of examples of this type of application. You can see here that, you know, this was a petroleum related facility where you had, this is kind of the CSM, you had the contaminated material that was, you know, in the subsurface. There's a sheet pile wall that has to remain permeable because they didn't want to create an issue with mounding of groundwater behind the sheet pile wall. So it was necessary to come up with some sort of a permeable absorptive material to limit, you know, the contaminants from reaching the water body. So at this particular site, they had the advantage that they were constructing a new bulkhead outboard of an existing old dilapidated bulkhead wall. So it created, kind of an ideal annular space, between the two walls where you could put some permeable material in and that could be used to intercept groundwater. So as you can see on the slide, this has been, in place for a number of years and has performed very well. We did put this material through some pretty significant testing up at University of New Hampshire to verify that the material would remain permeable even when saturated with the contaminants. Yeah, getting too excited here. Another example of a PRB design was put in, we supplied the materials. We're not the contractor. We're not doing the actual implementation work. We're supplying the materials. So I always have to clarify that when I say we. But this was an interesting project because actually three materials, but two sorptive materials were used as more of a treatment train approach. Here was a situation where they were concerned not just about NAPL or DNAPL, but also dissolved phase contaminants. So we used they used a combination of organoclay and activated carbon in a basically a treatment train approach to remove both the NAPL first and then take care of the dissolved phase. The second approach I'll talk about is what we call a horizontal funnel and gate. And a lot of people are familiar with the concept of a funnel and gate as it relates to a vertical permeable reactive barrier where you're trying to push groundwater through a vertical PRB. But we took that concept and basically turned it on its side when we look at a sediment groundwater type of a situation. So the concept here is that, if you have some residual contaminants that might be coming out of the ground, you can use a combination of a permeable treatment layer underneath a low permeability layer. And the idea is that as groundwater and or contaminants move laterally below that low permeability layer, the contaminant is being removed before the water ultimately comes out from underneath the layer. This was implemented at an MGP site a long time ago, and this was very heavily impacted sediment. We placed the AquaGate plus organoclay in a very thin layer. It was only about an inch thick layer initially on the sediment, and then it was covered with AquaBlok over the top of that, and then an aggregate cover material was placed over that. And this is sediment that was highly sheen producing. If you just touched it, you'd get kind of a bloom coming off of it. And I've followed up on this. There's no formal monitoring that's going on. It was all driven by visible sheen at this particular site because this is more or less a recreational side channel area along the Hudson River. And there has been no reported visible sheen from this area in that time frame. Another example of the same concept, the horizontal funnel and gate, is at a site down on the Arkansas River where materials were placed sequentially. First, organoclay was placed along a shallow shoreline area, and then AquaBlok was placed over the top of that. We actually did a number of different caps at this particular site using both AquaBlok and organoclay and combinations of it to take a look at what options might be available for more of a full-scale implementation. And that is going to move forward fairly soon. Approach 3 is kind of what I'm calling a combined low permeability layer with other types of materials. And this is where I'm going to talk a little bit about reactive core mat, other types of sorptive materials. There's a lot of ways to skin the cat here, and I want to make sure that I talk about some of these types of projects and activities. This was an MGP site where in Massachusetts, where they had a pretty unique problem in that they had a historic wall and they had seepage of contaminants coming from the base of the wall down into the canal. And because of the steepness of the slope, of course, our materials have an angle of repose. They have to be supported, you know, if you're putting them on a steep slope. So this was a good application for a reactive core mat, which is going to stay on a slope, you know, much better. But they had to address the toe, basically the toe of this wall, and try to minimize the amount of contaminant that was coming out from underneath the toe of that wall. So it was a, you know, think of it like, you know, applying AquaBlok like a caulking layer across the top of that, or the bottom of the wall, the top of the RCM, in order to try to create a seal there that would allow force the contaminant underneath the RCM where it can be effective. So pretty unique combination of the materials and to fit the site related constraints. The last approach that I'm going to talk about here quickly, it was touched on in the last in a couple of the presentations before, is this concept of ebullition driven, you know, contaminant migration. There have been a number of different sites, pretty noteworthy sites. I think actually the Chicago River is one of those, but there have been a number of other sites that were characterized by that. I think that's more common. It's fairly common. It's fairly common at MGP sites because of the microbial, the biologic activity in the sediments that, you know, create the gas release within the sediments. This is a design approach that was actually created by RMT, is now TRC. And the idea is that you can use a low permeability layer in connection with gas transmission layers to try to redirect any gas flow that is created underneath a capping layer. There have been 3 or 4 of these now that have been implemented at full scale. This particular project is in Ann Arbor, Michigan, at a former MGP site. And it was a situation where they did, you know, significant upland remediation, but there was still that residual that was contained in the area between where the upland was done and the river. And these were fairly impacted sediments. They did do a fair amount of removal of some of the sediments. The main river body is actually out here, and this is where some of the removal took place. But then they implemented this capping layer here, which was a combination of AquaBlok with gas transmission. And they actually installed some wells underneath so they could do some extraction. They could monitor actually what was going on underneath the cap and do extraction of any free napple if that ever took place. And you can see that this is the naturalized shoreline once the remediation was completed. So very, very successful project. Here I go again. So just a quick summary on the application side of things. Again, you know, the big advantage of these materials, I've talked about the idea of risk reduction, having some absorptive material in your cover layers that can address both sediment, you know, dredging residuals as well as the shoreline residuals. And you have a product in this particular case that you can handle just like sand and just like other cover or capping materials. And I think that's really important. It can be placed just like, you know, just like any other type of an implementation, remedy implementation. Quality control, as I've talked about, and knowing what's happening in the layer is really important. And we put a lot of emphasis on that. And finally, these materials We all know what's going on in the world with shipping and transportation and freight related stuff nowadays. And so it's important if you have large scale projects to be able to do remote manufacturing and create the materials near the site that you're actually applying the materials. And that's something that we've done on a number of different occasions. So we think we can keep it cost effective even for large scale applications. So I guess in summary, I talked about the two different materials and the different types of applications, how they can be applied in a real world application. So that's all I have. Thank you.